Right. Ready to dive into some pretty complex stuff today. We're going deep on recursion,
Oh yeah, recursion.
a concept that might seem like it's just for computer science folks, but
It goes way beyond that.
yeah, it has some big implications for philosophy too.
Absolutely.
You might be thinking, wait, isn't recursion just about those infinite loops you get in code?
Yeah, a lot of people think that.
But trust me, it
It
goes so much deeper.
really does.
We're going to be using the Stanford Encyclopedia of Philosophy as our guide today. So,
Great source.
yeah, tracing the evolution of recursive, from Dedekind
All the way to Gödel.
to Gödel, exactly.
It's a fascinating journey.
And for all you philosophers out there,
Get ready.
get ready to ponder some big questions.
About knowledge itself,
About the nature of knowledge.
the limits of formal systems.
Yes. The limits of what we can know, even.
It's really about understanding how recursion has shaped our understanding of what's computable. Can everything be solved by an algorithm? Are there hard limits to what we can define or even think about?
Okay, so let's start with something basic, something everyone knows.
Sure.
The factorial function, right?
Oh, of course, classic example.
Yeah, you multiply a number by all the whole numbers, less than it.
Like 4 factorial is 4 times 3 times 2 times 1.
Yeah, exactly.
It's a really clear example of recursion in math.
Okay, but so how does that work with recursion?
Well, think about it. The factorial of, say, 5, it's 5 times the factorial of 4,
Yeah.
which is 4 times the factorial of 3, and so on.
Right.
So you're defining something in terms of itself,
Yeah.
but in a way that always leads you back to a base case,
Okay.
like the factorial of 1, which is just 1,
Right.
that stops it from going on forever.
Okay, but, isn't that, like, a little circular? How can you define something by using itself in the definition?
That's a great question, and it's something that's puzzled people for a long time.
Yeah.
It's not a vicious circle, though. Okay. It's more like a set of carefully nested instructions.
Okay.
Each step brings you closer to that base case
Okay.
until the whole thing kind of clicks into place. Think of it like those Russian nesting dolls.
Oh, yeah.
Each doll contains a smaller version of itself until you get to that tiny one in the center.
Right, I see. So recursion has this, like, defined endpoint,
Yes.
which is what makes it actually useful.
Exactly. It has to stop somewhere.
Yeah, for computation.
Absolutely.
Okay, so now let's go back in time a bit
Let's do it.
to Dedekind,
Dedekind.
the brilliant mathematician who was really trying to figure out, like, how to establish a solid foundation for all of arithmetic.
He wanted to prove that math really works.
Yeah, like, proving that 1 + 1 actually equals 2.
Exactly. He wanted to be absolutely sure.
Wait, so they didn't just assume that?
Nope. They had to prove it from the ground up.
Oh, wow.
Mathematics is all about building from solid ground,
I see.
Dedekind wanted to define basic arithmetic, like addition and multiplication, in a really precise way,
Okay.
using set theory.
Using set theory.
And guess what he used?
Recursion.
Recursion. He was one of the first to really see its power.
So instead of just saying, addition's adding a number to itself over and over, he did something,
He made it precise.
yeah, more recursive.
Exactly.
Okay.
He gave these formal recursive definitions
Okay.
for addition, multiplication,
Showing how you could,
showing how you could build them up from the simplest case,
Okay.
defining each step, using the one before it.
like building a tower.
Yes, brick by brick,
Yeah.
making sure each one rests securely on the one below.
Okay, that's impressive.
Dedekind was a genius.
But it sounds like the story doesn't end with Dedekind.
Oh, it definitely doesn't.
Right.
There's so much more to come.
Yeah.
A Norwegian mathematician named Spolum came along and took these ideas even further.
Okay.
Yeah, he was fascinated by something he called primitive recursive functions.
Primitive recursive functions.
Yeah, it's a mouthful, but they're really cool.
Okay, so what are those?
Think of them as a special set of functions you can build from some very simple starting points, using, you guessed it, recursion.
Recursion, of course.
He realized that these functions could describe a ton of different mathematical operations.
So it's like Dedekind gave us the basic tools,
Yes, the foundation.
and then Skolem came along and said, okay, here's how you build all sorts of cool stuff with them.
Exactly. He showed us how to build these amazing mathematical structures.
Okay.
But what's really important here is that Skolem connected these recursive functions to something called effective computability.
Effective computability.
That's a big one.
Yeah, we should probably unpack that a bit.
Definitely. So effective computability, it's the idea that for a function to be effectively computable, there needs to be a clear step-by-step procedure,
Okay.
an algorithm,
An algorithm to get the output for any given input.
Right.
Okay, so like a recipe.
Exactly. A precise recipe that anyone can follow to get the same result.
Okay, so Skolem saw that these primitive recursive functions,
They fit the bill perfectly.
they fit this description
Yeah,
perfectly.
they're all effectively computable.
Okay, so then does that mean that all computable functions are also these primitive recursive functions?
That's the million-dollar question.
Yeah.
And it leads us to the next step in our journey. Gödel,
Ah, Gödel.
the legend himself.
I feel like everyone's heard of Gödel,
It's hard to escape him.
especially because of those incompleteness theorems.
Those are game changers.
But how does he fit into our story about recursion?
Gödel took the idea of recursion and just blew it wide open.
Yeah.
He refined the very definition of recursive,
Okay.
going beyond just the primitive ones that Skolem was working with. He called them general recursive functions.
General recursive functions.
Yeah, it's like he expanded the whole toolbox.
Okay, so he's basically expanding the toolkit here, right?
Exactly. He saw that there was more to the computational universe than just those primitive recursive functions.
Okay, but why was that important? Like how what he did different from what Skolem was doing?
Gödel realized that there were functions out there, perfectly calculable ones,
Okay.
that you couldn't define using just the tools of primitive recursion.
So he needed a more
He needed a more powerful definition.
yeah, to capture this whole range of what's computable.
Exactly. He saw the bigger picture.
Okay, so we have Dedekind kind of laying the groundwork,
Foundation.
Skolem expanding the toolkit a little bit,
Adding some powerful tools.
and now Gödel comes along and says, hold on, we need an even bigger toolbox.
There's more out there.
Yeah, there's more out there, and,
Yeah.
and creates these general recursive functions.
It's like climbing a ladder.
Yeah, climbing a ladder of increasingly complex ideas.
And this ladder, it leads us to some really profound philosophical questions about the nature of computation and what we can really, truly know.
This is where it gets interesting,
This is where things get really deep.
for all the philosophy folks out there.
Yeah, your thinking caps on.
Yeah, but before we jump into that, can you give us a little more on these general recursive functions? I'm still trying to wrap my head around what makes them different
I understand.
from those primitive ones.
It's a subtle but important distinction. Okay, so think of it this way. Gödel's definition is like saying a function is general recursive. If you can build it up from just a few simple building blocks using a really specific set of rules.
Yeah.
And these rules include things like composing functions.
Composing functions, okay.
So you're taking two functions and you're sticking them together to make a new one.
Right.
And then there's something called primitive recursion, which we already talked about.
Yeah.
Which is, it's a controlled way of letting a function refer back to itself.
Right, like that factorial example.
Exactly, like that factorial example.
Okay.
So it's all about building up complexity in a really systematic way.
I see. So Gödel's definition is broader than
It's more inclusive.
just those primitive recursive functions that Skolem was talking about.
Exactly. Captures more of that computational universe.
Okay, and this leads to something you called Church's thesis.
Ah, yes, Church's thesis.
Another big name.
A big one.
What's that all about?
So Church's thesis, it basically says that any problem that can be solved by an algorithm,
Go on.
any effectively calculable function, is also a general recursive function.
So it's like saying that Gödel's definition really nailed it.
Yeah, it captures the essence of what it means to be computable.
Okay, captures the whole realm of what's computable.
That's the idea.
Wow.
It's a really bold claim.
Yeah.
And it hasn't been formally proven,
Right.
but it's held up incredibly well over time.
Okay, but how does this all connect to the limits of knowledge?
Right, that's the big question.
You mentioned that earlier, and I'm really curious about the philosophical implications.
Absolutely. So if Church's thesis is true,
Okay.
then any problem that can't be solved by a general recursive function is inherently unsolvable.
Whoa.
No algorithm, no matter how clever,
Okay.
could ever crack it.
So there are problems out there that are just like fundamentally beyond our reach.
Yeah.
Computationally speaking.
It seems that way, yes.
Wow. Well,
And this is where Gödel's incompleteness theorems really come into play.
yeah, the incompleteness theorem.
They're like bombshells dropped right into the world of mathematics and logic,
Yeah.
with shockwaves that reach into philosophy as well.
They're super famous, but also famously difficult to understand.
Yeah, they're mind-bending.
Can you break them down for us?
I'll try my best.
Okay.
So imagine you have a formal system for arithmetic.
Yeah.
This is a set of axioms and rules
Right.
that you hope will let you prove all the true statements about numbers.
Okay, you wanna prove everything that's true about numbers
Exactly, that's the goal.
using this system.
Right, and Gödel's first incompleteness theorem comes along and says,
Oh.
no matter how good your system is,
Hmm.
there will always be true statements about numbers that you can't prove.
Wait, so even with a perfect set of rules, there are still things that are true
There are true things that we can't prove within the system.
about numbers.
Yeah, that we just can't access using those rules.
That's kind of unsettling.
It is. It's a bit of a blow to our hopes for a complete and consistent mathematical system.
Yeah.
And then it gets even weirder
Oh no.
with the second incompleteness theorem,
Okay.
which says that a consistent formal system of arithmetic can't even prove its own consistency.
So it can't even tell us
It can't guarantee that it won't contradict itself.
that it's not going to like break down.
Exactly. And that seems
It's
like
pretty basic requirement.
a pretty fundamental thing you'd want from a system that's supposed to be about truth.
Yeah, for sure.
But the Gödel showed us that even that is beyond reach.
Okay, so Gödel's theorems are basically exposing these inherent limitations
Fundamental
on
limitation.
formal systems.
Yes.
Right? There are boundaries to what we can capture
Boundaries to what we can express.
and prove using these systems.
Precisely.
Okay, so where does recursion fit into all of this?
Right, back to recursion.
Yeah, it feels like we took a little detour
We did, but it's all connected.
into some pretty abstract territory.
It is, but it's important territory.
Okay.
Because recursion is at the very heart of Gödel's proofs.
Okay.
He used this really clever technique called Gödel numbering,
Gödel numbering.
where he basically represented formulas and proofs as numbers.
Okay.
And what do you think was crucial for manipulating those numerical representations?
Don't tell me recursion.
Recursion, you got it?
It's those Russian nesting dolls again.
They keep coming back. So Gödel used recursive functions to encode and decode those numerical representations.
Code.
This allowed him to talk about the properties of the formal system within the system itself,
Right.
which is absolutely key to showing its limitations.
So recursion, it's not just a tool for like building complex math,
It's a tool for understanding math itself
but it's also a key to understanding the limits of our systems of knowledge.
and the limits of our thinking.
That's a pretty mind-blowing connection.
It really is.
It really is.
And the philosophical implications are huge. If
Yeah.
there are mathematical truths that we can never prove,
Right.
what does that say about the nature of truth itself?
Yeah.
What are the true boundaries of human knowledge?
These are big questions.
These are questions that philosophers have been grappling with for centuries.
Yeah.
And Gödel's theorems just add this whole new layer of complexity to the debate.
It's like recursion has taken us on this journey from simple calculations
From the simplest
to the very foundations of what we can know
and what we can even imagine knowing.
and understand.
It's a pretty amazing journey when you think about it.
It is.
And there's still more to explore.
Oh, there's always more.
The world of computability theory is full of these fascinating ideas like decidability, the halting problem,
Okay.
different levels of undecidability.
Decidability, halting problem. I'm sensing another deep dive coming on.
You're right on the mark.
Yeah.
But before we go further down that rabbit hole,
Right.
let's give our listener a moment to process
Yeah.
everything we've covered so far.
It's a lot to take in, I know.
It really is, but it's worth taking the time to ponder these ideas.
Absolutely. Okay, so we've explored how recursion shapes our understanding of what's computable, but
Yeah.
you mentioned this concept of decidability.
Yeah. Decidability.
What exactly does that mean?
Decidability is all about whether or not we can answer a question definitively using an algorithm. You can think of it like a judge in a courtroom that can always give you a clear yes or no verdict.
So if a problem is computable, meaning there's an algorithm that can solve it,
Right.
is it automatically decidable too?
That's a great question, and it's not as straightforward as you might think.
Okay.
A problem can be computable, meaning we can calculate the answer,
Okay.
but it might not be decidable, meaning there's no algorithm that can always tell us whether the answer is yes or no.
So there's a distinction there.
There is a subtle but important one.
Can you give us an example?
Of course.
I think an example would be helpful.
So let's consider the halting problem.
The halting problem.
It's a classic.
Yeah, I've heard of this one.
It asks, given a program and its input, can we always determine whether that program will eventually halt?
Halt meaning.
Meaning it finishes its computation
Okay.
or whether it's going to run forever.
In an infinite loop.
Exactly, an infinite loop.
Okay.
So will it stop or will it go on forever?
That sounds like a pretty fundamental question.
It's crucial for anyone working with computers.
Right.
And here's the mind-blowing part. The halting problem, it's undecidable.
Undecidable.
There is no algorithm that can solve it for every single program and input.
So there are programs out there that we can't even figure out if they'll ever stop running.
That's right. We can't predict their ultimate fate.
That's crazy.
It has profound implications for computer science.
How so?
Well, it means there are limits to what we can automatically verify about programs. We can't just write a program that will tell us with absolute certainty whether another program will behave the way we expect.
It's like hitting a wall
Yeah, like a fundamental limit.
to what we can know about computation.
You got it.
Okay, so if the halting problem is undecidable,
Right.
does that mean that all problems are undecidable?
Thankfully, no.
Okay.
There are plenty of problems out there that are perfectly decidable.
Okay.
We can write algorithms to solve them and know for sure what the answer will be. But there's this amazing thing. It's called a hierarchy of undecidability.
A hierarchy.
Yeah, like levels of undecidability.
Okay.
Some problems are undecidable in kind of simple ways, while others are undecidable in ways that are just, well, much more complex and mind-boggling.
A hierarchy of undecidability. That's a lot to wrap my head around.
It is. It's like layers upon layers of the unknown.
Okay, so how does this hierarchy work?
Well, it's a fascinating area of research, and what's really remarkable is that this hierarchy mirrors the arithmetical hierarchy.
The arithmetical hierarchy, the one that classifies sets of numbers.
Exactly, based on the complexity of their definitions.
So there's this deep connection between how logically complex a problem is and how undecidable it is.
That's the idea. The more complex the problem, the more likely it is to be undecidable.
So it's like the limits of what we can compute
Yes.
are kind of tied to the limits of what we can even express and define using formal languages.
Exactly. It all comes back to logic, mathematics, and computation. These fundamental concepts are all intertwined.
Wow, this deep dive into recursion has been a real roller coaster ride.
It has, hasn't it?
We've gone from simple factorials to the foundations of arithmetic to undecidability and the very limits of knowledge itself.
It's quite a journey.
It is, and I think it highlights just how powerful and profound this concept of recursion really is.
It's a concept that forces us to confront the boundaries of what we can know and what we can compute.
Absolutely. It's a reminder that even in the realm of pure logic and mathematics, there are still mysteries to be explored.
Mysteries that might always remain just beyond our grasp.
Well, dear listener, we hope this exploration of recursion has left you with a sense of wonder and a thirst for more.
There's so much more to discover out there.
Perhaps recursion holds the key to unlocking even deeper mysteries about the nature of consciousness, the fabric of reality itself.
Who knows what other secrets recursion might hold?
That's something for you to ponder.
Keep questioning, keep exploring.
Until next time, keep seeking knowledge, keep asking questions, and keep diving deep.